Hello students, let us begin chapter 5. First, let's begin with a review. In the previous chapters, chapters 2, 3, and 4, we used to study this kind of equations, linear ordinary differential equations with constant coefficients. And what did you used to do? Take Laplace transform of both sides, right-hand side is highlighted in red, and then use the linearity property of Laplace transform so that we can decompose the left-hand side. Does it work? Yes, it does. Laplace transform is basically an integral. It was defined using the integral, and integrals satisfy this linearity property. We can separate the addition and then pull out any constant coefficients. Repeat it n times, and then we're going to get this. Now what? What are the Laplace transforms of the derivatives? Well, this is a Laplace transform of the nth derivative. How do we prove it? Just apply the integration by parts repeatedly n times. This one is the Laplace transform of n minus first derivative, and so on and so forth. That of the second derivative, that of the first derivative, and then the original, so small y became capital Y. And the right-hand side, small f became capital F. Now what do we do? Let's rearrange these things a little bit. Let's get all the y parts together so that we have this kind of situation here, which is highlighted in blue. How did you get that? Let's go back to the previous expression here, and an times s to the nth power, an minus 1 times s to the n minus first power, and so on and so forth, a2 times s squared, a1 times s to the first power, a0 times 1, which is a to the s to the 0 power. Put all those together and we get this expression, which corresponds precisely with the original linear differential equation here. Nth derivative corresponds to the nth power, n minus first derivative corresponds to n minus first power, and so on and so forth. This part is called a characteristic polynomial, as a matter of fact. By the way, how about the brown part? Well, all the y0, y prime of 0, all the way to y of the n minus first derivative of 0, all those are constants. So put all those together, add, subtract accordingly, then you're going to get a polynomial of s. That's going all the way over to n minus first degree. So we have n minus first degree polynomial of s. And we can solve for y like this. Polynomial part here, brown part, and red part is coming from the right-hand side. I mean, this f of t is becoming capital F of s. And then the denominator is the characteristic polynomial. Now, if we take the partial fraction and then take the Laplace inversion of each decomposed partial fraction, then you're going to get what you want. Elementary, but really tedious. So let's exemplify a little bit. I just made up a problem. Let's begin with something like this. Brown part is like this, and the red part, which is the Laplace transform of the original right-hand side here, and then the denominator, the characteristic polynomial, can be factored accordingly, and I took rather typical factorization here, some linear factors to the certain power, and some irreducible quadratic factor to a certain power. We cannot have anything else because of the fundamental theorem of algebra. And here is the decomposition by partial fraction. Let's look at the red one here. It goes up to first power, so we have one of this. Now blue part, second power, so we have two of these. Green power, we have third power, so we have three of those. Purple part, we have second power, so we have two of those. All these, red, blue, and green, those have a first degree polynomial to a certain power in the denominator, so the numerator is 0 degree, just constant. How about the purple part? We have quadratic second degree polynomial down here to a certain power, And so numerator has to be the first degree polynomial. Quite typical. That's the theory of partial fraction. And then solve this linear equation, system of linear equations accordingly using help of computer or something, or maybe use some computer algebra system like a part command directly, then you're going to get the decomposition. And then if we apply that Laplace inversion term by term, we are going to get the solution. And I didn't identify those constants, A1, B1, B2, C1, C2, and so on. You can, but it will be really tedious numbers. But in any case, you're going to get this kind of answer. As I said many times, very, very tedious, but in terms of theory, no big deal. And in terms of computers, no problem at all. Computers are really good at doing something tedious. Well, that was a quick review. And let's go over to an overview of what's to come. In this chapter, we're going to be concentrating upon this kind of equations. Linear ordinary differential equations with variable coefficients. What's the difference? Here, all those A1, A2, all those are constants. Here, those can be functions. Now, can we do the same thing? No, not really. We can take Laplace transform. Okay, so far so good. But the second, this one doesn't work. Is it possible to separate the addition? Yes, you can. Laplace transform is integral, so yes, you can. But we cannot take the coefficients out. If it is a constant, we can take it out, yeah. If it is a function, no, we cannot take it out. So Laplace transform, this one doesn't work, at least in current stage. We may need some further adjustment, but at this stage it doesn't work. So we'll have to find something else to do. And that's basically what we are going to do in this chapter. By the way, here are some well-known examples. Bessel's equation, which typically shows up whenever you deal with a cylinder. And Laguerre's equation, I'm not exactly sure about that. Legendre equation, and that's something that appears typically when you deal with spheres or balls. Chebyshev's equation, Hermite's equation, they're all well-known equations with some rich history, but I don't think we are going to deal with any of those. Too complicated, as a matter of fact.